In this video, we're going to talk about Cavalieri's principle. In order to see it, let's start with an example of these two stacks of coins, stack A and stack B. First, we're going to talk about how the coin stacks are different from each other. You might want to pause the video to think about it and then unpause when you have your answer. One of the stacks of coins is standing up straight, and one of the stacks of coins is tilted or slanted. Stack A represents a geometric solid. You might want to pause the video and think about what it is, and that would be a cylinder. Stack B can also represent a cylinder. It's just a cylinder that is tilted to the side. How do the heights of the two stacks compare? You might want to pause the video and think about it and unpause when you have an answer. The heights are the same. And that's because there's the same number of coins in each of the stacks. So since it's the same amount of coins high, they're going to have the same heights. The last question is, how do the volumes compare? You might want to pause the video for that. Well, to find the volume of a cylinder, we need to do the area of the base times the height. Since the bases are both circles, specifically the coins, and since the coins are the same, they're going to have the same areas, and since the heights are going to be the same, they're going to result in the same volume. In fact, any coin that you pull out from either of these stacks is going to have the same area. So we call that a cross-section. Any cross-section that you pull out from that you slice out from either of these two stacks, any coin will have the same area. And since they will have the same area, and the solids have the same height, they're going to have the same volumes. And that is going to be what Cavalieri's principle is when we see it on the next page. Before we move on, we have some fancy words for these two stacks of coins. We call stack A right solid or a right cylinder because it's standing up straight. There is a right angle perpendicular to the base. And we call the stack an oblique solid or an oblique cylinder because it's tilted or slanted to the side. And for oblique solids, just something to keep in mind, often the height, the altitude that we measure height by is located outside of the shape. As we were talking about with the stacks of coins, Cavalieri's principle says that if we have two solids that have the same height and we slice out a cross-section by parallel plane, so we take out a cross-section from either of the two, and the cross sections have the same area, then the two solids are going to have the same volumes. So once again, same area of cross section, same height, equal volumes. And that's what Cavalieri's principle states. We're going to take a look at the pairs of solids in the following chart. And for each one, we're going to decide if the volumes are the same. And we're going to use Cavalieri's principle to support whether we're saying if the volumes are the same or not the same. You might want to pause the video, think about each of the pairs, come up with your own reasoning, and then unpause the video to see the answer. For the first one, the area of the base, because capital B represents area of the base. So the area of the circular base is 12. And if I take any slice of the cylinder going in that same direction, horizontal, parallel to the base, it's going to result in the same circle. And it's going to have the same area as the base. So the cross-sectional area is going to be 12. On the prism, the area of the base is length times width, which is 12. And I'm a horrible artist, but any cross-section that you take will be the same rectangle with the same area of 12. I should say any cross-section parallel to the base, going in the same direction. So since the area of the cross sections are the same for both of the solids, they're 12, and since the heights are the same, they're both 6, they're going to have equal volumes according to Cavalieri's principle. So I'm going to write here same volumes. And notice that these are different solids. It doesn't matter. As long as the area of the cross sections are the same and the heights are the same, according to Cavalieri's principle, they're going to have the same volumes. If we take a look at number 2, I notice that the height on this oblique cylinder is 7. It's measured by the altitude. Be careful. This is the slant height. It's not the real height, that 10. We measure height by an altitude, by a perpendicular line, because it's how tall something is. So we measure it by a right angle, by a perpendicular line in altitude. So always look out for that right angle. A lot of questions will do that to trick you. They'll have like the fake height, the not real height, the slant height, but you need the real height, the altitude, the perpendicular line for volume. And the height on this right cylinder, since it is perpendicular to the base, that is the actual height. So the height on this cylinder is 10. So since there's different heights, they can't have the same volume according to Cavalieri's principle, because Cavalieri's principle is same heights, same areas of cross-section, same volume. So if one part of Cavalieri's principle, the heights part, is not satisfied, we don't even have to move on to check the areas of the cross-sections, because we already know it's not going to have the same volume. So I'm going to write here, not same height, unequal volume. If we take a look at number 3, the heights are both 5 on the cones, and they're both cones. One's a right cone and one's an oblique cone, but the heights are both 5. So now we just need to check the area of the cross section. Wait. And the cross sections will be circles. So these will have the same volume. And we don't really have to look much further because they're both the same shape. So they're both going to have volume found the same way. If they have the same heights and the same radius, they're going to have the same volume because it's going to have the same area of the cross section, the same area of the base. But if they weren't the same shape, then we would have to look a little bit further. Okay, number 4. For number 4, let's check out the heights. So the height of this prism is 5, and the height of this prism is 5. So far, so good. And then we need to check out the area of the cross section. So cross section here parallel to the base is going to be a triangle. And I'm a terrible artist, but they're all going to be the same triangles. Area of a triangle is 1/2 base times height. The base and height of the triangle are 4 and 3. So that's going to be 6. And this base is a rectangle. And the rectangles throughout, if we slice parallel to the base, length times width, the area of those rectangles are 6 times 1, which is 6. So same height, same areas of the cross sections, we're going to have same volumes. So I'm going to put here same volumes. Okay. And also, I'm going to backtrack slightly. Here, we did have circles as the cross section, but notice how the circles get smaller as you approach the apex. So even though these have the same heights and the same radius, the cross sections change as we get closer to the apex, to the point on the cone, they get smaller. So they're not all going to have the same areas. So I'm actually going to change this to not the same volume according to Cavalieri's principle, because if the circles are smaller, then they're not going to have the same area as each other. It doesn't have a constant cross section. Okay, for this, the base is a square. And if we cut parallel to the base, it will still be squares, but notice how the squares are getting smaller. Same thing here as well. I'm a terrible artist, but the squares are getting smaller. So even though we have the same heights and maybe the same area of the base, it's not going to be the same volumes because it's not the same cross section as we go towards the top. So the area of the cross section can't be the same. And Cavalieri's principle says if the areas of the cross sections are not the same, then they can't have the same volume. Not same volume. For this one, the cross sections are all the same circles. For this one, they get smaller. So we can't have the same volume. Because the cross sections are not constant, even though they are on the cylinder. On the cone, the circles get smaller as we approach the apex. So there's no way that all the cross sections can have the same area as the cross sections of the cylinder. Sue believes that the two cylinders shown in the diagram below have equal volumes. Is Sue correct? You might want to pause the video, write down an explanation, then unpause when you have it to check your work. Notice how in the cylinders, and let me draw a little bit better. It's the same circles. Even in the slanted one, it's the same circles throughout. So it's a constant cross section as you cut it parallel to the base. So the area of the cross sections, since they're circular cross sections, will be pi r squared. And they do have the same radius of 5. So the area of the cross sections will both be 25 pi. And the height is both 11.5. According to Cavalieri's principle, solids must have same cross-sectional area and same heights to have the same volume. Since the areas of the circular cross sections for both cylinders are 25 pi and the heights are both 11.5, Sue is correct that both will have the same volumes. When you're answering Regents questions like this, a good idea is to use information from the question in your answer. We have one more Regents question for this video. So the diagram below shows two figures. Figure A is a right triangular prism and figure B is an oblique triangular prism. Use Cavalieri's principle to explain why the volumes are equal. So they already tell us that the volumes are equal. We need to use Cavalieri's principle to explain. You might want to pause the video, write down your own explanation, and then unpause to check your work and see the solution. So since it's a prism, it's going to have a constant cross-section because no matter where you cut it parallel to the base, in a prism, the cross-section is going to be the same as the base. So since the base is a triangle, no matter where I slice it, as I go up, they're going to be the same triangles. And the same thing's going to result here, even though this is oblique. Sorry, I'm really bad at drawing slanted. But it's going to be the same triangle, no matter how you slice it, the same as the base. So we have constant cross-section. So now we just need to check out the heights and the cross-sectional areas. Let's start with the heights. The heights of both are 14. So far, so good. And even with the oblique one, the height was 14, so that was good to go. I'm just going to erase this so we could see a bit better. And we know that this 14 is the real height because it does form an altitude. So far, so good. So now we just need the cross-sectional area. So the cross-sections are triangles. So the area of a triangle is 1/2 base times height. For the one on the left, we have 1/2. the base is 8, the height is 5. And for the one on the right, we have 1/2. The base is 5, and the height is 8. And since we're multiplying the same numbers together, it's going to result in the same thing. 20. I'm going to write the same thing as I did before. According to Cavalieri's principle, if solids have the same cross-sectional areas and the same heights, they have equal volumes. Since both triangular prisms have heights of 14 and cross-sectional areas of 20, they have the same volume. And that would be perfect for this question.